Alrighty, here we're going to explore using deep learning approaches to detecting osteoarthritis in radiographs. And so given x-rays of a patellar joint, so like the knee in humans, can I use deep learning techniques to detect and diagnose OA? And the data that I used, I got from Kaggle. There's a really good knee osteoarthritis data set with severity grading. The URL is there. In the future, I would love to make a collaborative veterinary database and expand this project, because I think that I could make a tool that goes across species. The process here, EDA, created a convolutional neural network, a recurrent neural network, made some comparisons, some revamped versions, and we will continue on through that. So the EDA here, we're looking at the basic counts per class per split, so that's going to be this right here. And then this is a sample of the images that I'm working with and their associated OA grades. That's a human diagnostic situation, but it's a 5-point scale with 0 being no arthritis and 4 being the worst arthritis, is essentially the best way to determine that. I also confirmed all of the image sizes were the same at 224 by 224. And then I created this initial CNN model with 3 convolutional layers, trained it on 30 epochs. It wasn't the best performance when we're classifying into the 5 grades of human OA, with a test accuracy of almost 53%. So that's that one. And then I did, though, collapse my models to a binary diagnosis of healthy versus arthritic, because the data that we have for humans and their accuracy at reading OA radiographs is for healthy versus arthritic. So I will be comparing that later on. So for this initial CNN model, this is what we've got going on. And then I did a recurrent neural network model as well. It fully trained in only about 2 minutes, which was a massive red flag. And then looking at this heat map, you can see that it created a trivial classification where it dumped everything into one incorrect mostly category. So it's not great for this purpose. I did still collapse it to binary so that I could compare it on the off chance that when collapsed it compares to humans. Probably will not, because the PPV is undefined, but just to have the data. And these are the human metrics. So this is based on the only journal that I could find that had this for specifically reading knee osteoarthritis data, the accuracy of human diagnosticians. So overall 73%, PPV 88, MPV 66. You can see the data there. If you're interested in reading the full journal, the URL is right there, or I have all of my references listed at the end of this presentation. And these slides will be available on GitHub if you would like to look at them more thoroughly. Initial comparisons, here's what we've got. The RNN model, as expected, did absolutely garbage. But the CNN model is actually really close. It's only 1% lower in accuracy than the doctor themselves, and it has a higher sensitivity and very close on the PPV. So I wanted to see, can I beat it? Can I improve above human accuracy? And so I made a second CNN version with improved data augmentation, class weights, deeper filter size, additional epochs. And here's what I got. And it did actually do a lot better. We have a much more diagonal confusion matrix heat map. So looking at it as binary, here's what we have as well. Again, showing a lot better. And I did do some more I put all of the comparisons together, as you can see here. And this wasn't exactly what I expected to see. I had thought that perhaps overall accuracy might go up. So I decided to dig a little deeper and do some confusion breakdowns, where I found that my changes created a trade-off situation where the second version missed fewer cases of OA, while the first had fewer false positives. And so I determined that the next step should be to tune the decision threshold, because this is standard practice with radiology AI, pathology AI, and other clinical applications. Seeing as we're looking through a radiological lens, it made sense. It's going to compensate for model biases, and in practice, tuning the decision threshold allows the CNN to transform from a classification experiment to a diagnostic tool. And here's the results of my tuned CNN2. And here are the overall diagnostic performances that I will discuss in depth in the next slide. Feel free to, again, these slides are going to be available on GitHub for anyone who possibly wants them to download. And here's the discussion. So looking at that first CNN model and the tuned second CNN model, they're comparable with human doctor baseline results. The raw CNN version 2 did lose some accuracy because it favored sensitivity. And I want to actually discuss, speaking of sensitivity, all of these metrics a little bit more, and because it provides more meaning to what the results are. So in this instance, sensitivity is the ability to actually detect the arthritis. And the best for this was actually the raw version 2 of the convolutional neural network, and closely followed by the raw version 1 of the CNN. However, the tuned version 2 still performed higher than the human level. Specificity is going to be the ability to detect healthy joints. And humans scored the highest here at 92%. And while the machine learning performers did not perform quite as well, the tuned CNN version 2 was very close. It scored a respectable 86%. Without tuning, however, the second convolutional neural network scored the lowest in this category. And that shows that without tuning, it's likely over-predicting instances of OA. So then we move on to the positive predictive value, or the PPV, and that's the chance that the knee is actually arthritic if the model predicts it to be arthritic. So once again, humans still are scoring the highest at 88%. However, my tuned second version of CNN was able to score extremely close behind at roughly 87%. And then finally, we're going to look at the negative predictive value, which is the MPV, and that's measuring how reliable is a healthy prediction. Humans are actually not very reliable in this instance, but they did still score the best. However, all of the CNN models, so essentially all of my models, if I throw out the RNN, scored all above 55% in this metric. So it is reasonably close to human performance. An important note that the RNN did not appear in the categories of sensitivity and PPV, as it collapsed to be a trivial classifier, as I stated before. As you could see on those heat maps, it only categorized into one category, which gives a perfect specificity, but horrible sensitivity and no true positives, so the PPV ends up being mathematically undefined. It's therefore considered, I consider it to be anyway, an inappropriate method of classification in this instance. Future applications, implications, and takeaways. In my opinion, the tuned second CNN iteration shows the most promise. It was able to achieve nearly human-level confidence with positive diagnoses, and while it did favor sensitivity over specificity, I believe it to be the best baseline for future iterations of applying deep learning approaches to radiographic OA diagnosis of the patellar joints. My hope is to adapt this model for future use on radiographs of canine and equine, in particular patellar joints. Those are going to be the dog and horse analogs to the human knee, respectively, once an appropriate data set can be sourced. Potential further refinements. So if I had more resources, including a stronger, higher powered computer, more time to invest into this research, etc., these are some of the things that I would consider looking into to further improve my models. I would look at different methods for cropping the images, possibly employing even a simple bounding box or a separate segmentation model. Higher resolution images, if I could source those, that would be fantastic. Research of different effects of various methods of ensembling and pooling methods, and addition of certain residual connections. A larger and more diverse data set is the goal. Greater computational power would really allow would allow my models to be stronger, because I could employ a stronger GPU to experiment with higher resolutions, larger batch sizes, deeper models, and it would run faster. And then I would really like to also acquire more data on human accuracy instead of simply relying on the singular study I was able to find. I would love to instigate my own study into the matter to personally have more confidence in my own baseline data. If I had unlimited time and resources, I would absolutely go down that route. Here are my references.